Welcome to lesson 9 of this course on industrial automation and control. Today we will be talking about signal conditioning. As we have discussed right in the beginning, that the basic signal from the sensor needs to be changed, needs to be processed, needs to be amplified, needs to be stripped of undesirable elements like filtered. So several operations need to be done on the signal from the sensor to be able to finally extract the value of the process variable accurately over time. So all this is under signal conditioning, and after this, going through this course, one should be able to describe a very important signal conditioning circuit called the Wheatstone's bridge, which is widely used for resistive and capacitive sensors, also for inductive sensors in some cases. Then after, so this typically gives you a voltage signal, and this voltage signal is generally low level. So this needs to be amplified, and there are various types of amplifiers which one can use. So we will go through the various kinds of amplifiers and learn the structure and function of them. Then we also need to use various kinds of filters typically for noise filtering, and also sometimes for separating out the data. I mean the parts of signals which are unnecessary but which were required for let us say modulation. We will see that. Then and lastly we will learn about some, apart from amplifiers and filters, we will also learn about some miscellaneous types of circuits which are also very important. So we have chosen 2 of them. There are actually a wide variety of circuits which can be used, all of them cannot be covered. So we have chosen 2 classes. One is that one are sample and hold amps, and the others are phase sensitive detectors, which are very important in instrumentation. So we go into the lecture Wheatstone bridge. The Wheatstone bridge structure, as we are seeing, in this case the bridge is drawn for 4 resistive elements. So this is the source. There are 4 resistances. This is the so called detector, and in the case of the in an instrumentation setting, generally what is done is that this bridge is operated in the unbalanced condition. That is, as we can easily realize, that the voltage between the C and D points depend on the resistance ratios, right? So when the resistance ratios are equal, that is R2 by R3 is equal to R1 by R4, in that situation the voltage between C and D is going to be 0. Now in the instrumentation situation, suppose one of the sensors, suppose this is the sensor whose resistance varies with some process variable that we want to measure, suppose it is temperature. So then we design the resistance in the other resistances in such a manner that at some reference temperature this resistance is going to be such that the resistance ratios will be equal and the bridge output will be 0. Now as the temperature will change from that reference temperature, then this resistance is going to vary. So the resistance ratio will no longer remain equal, and therefore some voltage will appear between the C and D points, which we will typically feed to some amplifier and some downstream signal processing circuit, right? So we essentially study how we essentially process this unbalanced voltage of the bridge. Now if you see the behavior of the bridge, so if you see an analysis, then obviously from the previous diagram you can make out that the voltage between the C and D points, which is typically fed to the amplifier, or which is the output of the bridge, So we can call this the V output for the bridge. That is given by, it is easily found out, that is given by 1 by 1 plus R3 by R2 minus this. Now suppose R1 is the resistance which is varying. So then this R1 will be changing, and therefore the output voltage will be varying. And it turns out that, see, in this case you can find out that the output voltage is actually a nonlinear function of R1, but if R1 is typically very small, then it turns out that the output voltage becomes proportional to the change in R1. So it is linear over a certain range. For example, and this kind of Wheatstone bridge is actually used in various configurations in instrumentation. For example, you can connect a single strain gauge into the bridge. So then the strain gauge forms one arm of the bridge, and with applied force or pressure, strain is created, and therefore the resistance of the strain gauge will change, as we have learnt in our previous lectures, and therefore the output voltage will change. Now this is typically this is mentioned as E Thevenin, because, or rather EOC, or the open circuit voltage between the V and CD points. Now it is generally considered open circuit because the impedance that is generally connected, that is these two terminals C and D, are actually connected into an amplifier whose input impedance is generally quite high, much higher compared to the resistance values themselves. Therefore the voltage between C and D can be considered as the open circuit voltage, or the Thevenin's voltage. So that is why it is mentioned as E Thevenin. It turns out that this E Thevenin becomes proportional to this G is actually, you know, delta R by R of the strain gauge. So it will be proportional to delta R by R of the strain gauge. So, and since delta R is actually proportional to strain, so therefore eventually the output voltage is actually going to be proportional to the strain. So this is how the strain gauge incorporated into a Wheatstone's bridge produces an output voltage which is proportional to the strain, right. Now similarly we can actually so if you have another kind of another sensor which is also used with a Wheatstone's bridge is the resistance temperature detector. So if you have a single resistive sensor temperature detector, then we are interested in measuring temperature, and again the delta R value, that is the change in resistance for a given change in temperature, is given by this R2 alpha delta T. So therefore you will find that again the output voltage is actually proportional to the change in temperature. So it measures the temperature. Now in certain cases we can put two sensors in a bridge. So in such a case it happens that so you see, this is, suppose we are interested in measuring the temperature difference between any 2 points in a process. So at one point we put one RTD, at another point we put another RTD, and those two RTDs have been incorporated in the bridge in these two arms. So then the resistance of first RTD varies like this: R1 equal to R0 into 1 plus alpha T1, and similarly R2 is equal to R0 into 1 plus alpha T2. So therefore it will turn out that the output voltage, or the E Thevenin, is given by this, right. So you can see that the voltage is now becomes proportional to T1 minus T2. So we can create a voltage which will become proportional to the temperature difference which we want to measure. So this is possible. Similarly, if we can also put 4 sensors into a resistive bridge, right. So this is, for example, typically used, as we have already seen, in strain gauge load cells. So if you put all the 4 all the 4, only thing is that we have to only ensure one thing, that is we have to ensure, you see, that if these 4 resistance, how is the voltage produced? The voltage is actually produced by unbalancing the ratio of the two arms. So as the resistances change, we must connect the resistances in such a manner that the ratio actually changes, right. So it should not be that R1, R4, R2, R3 are all changing in the same direction in the same ratio. If that happens, then we are not going to get any output voltage. So typically, as we have seen in the case of strain gauges, we put the strain gauges in such a manner that if R1 increases, R4 will decrease, and even to increase the sensitivity, we put it in such a manner that R2 will increase and R3 will decrease. So what will happen is that this bridge ratio is going to go up because R2 is increasing, R3 is decreasing, and this bridge ratio will go down because this is decreasing and this is increasing. So therefore the voltage difference between the C and D points is going to be equal to the sum of these resistance changes. So we set up these resistances in a clever manner, and how we set up that we have seen in the case of the other sensor related lectures, that we set it up in such a manner that all the resistances changes add up to the output voltage, and therefore we get an increased sensitivity. So we get a higher value of output voltage from the bridge. So it turns out that in this case that the output voltage, see in the single sensor case, you had an output voltage which is Vs by 4, the sensitivity into delta R by R. Here you are getting Vs into delta R by R, because the individual all the resistances are actually contributing to this resistance imbalance, and so you have got a 4 times sensitivity. So typically by using a 2-arm bridge, there are 2 advantages. One is that the sensitivity is doubled. Second is that non-linearities, as we will see, are typically cancelled. So therefore we can operate the bridge linearly over a much larger of resistance variation. Similarly, if we have 4 resistances, then the sensitivity is further increased. Also you can see that if for example in a strain gauge, the resistance changes due to 2 things. One is the strain itself, which we want to measure. The second thing is that it can also change due to ambient temperature variation. But interestingly, the resistance change due to ambient temperature will be in such a way that all these resistances will actually increase. So therefore the resistance changes due to the temperature is not going to affect the bridge ratio, and therefore we can make our bridge output voltage completely insensitive to the variation in the temperature. This is also another advantage of having a push-pull configuration and a 2 or 4 arm bridge. So having said, so this is why the strain gauge is actually very popular and I mean extensively used in instrumentation. Similarly, it is not only that resistive sensors can be incorporated into strain gauge bridges. Actually this theory that the output voltage is depending on the bridge ratio is true for general impedances. So therefore we can instead of resistances, we can also have capacitive sensor where you have a capacitance C1 and you have a capacitance C2, and therefore this is C1 and this is C2. So typically for capacitive sensors we often set up, as we have seen in the case of displacement measurement, that we set it up like a parallel plate capacitance. So this plate is moving. So what will happen is that C1 will become C1 plus delta C1, and C2 will become C2, rather C1 plus delta C, and C2 will become C2 minus delta C. So typically sensor configurations are such that there is an equal and opposite change in the resistance. So naturally the bridge voltage is going to be proportional to this delta C, and it is going to be considerably linear. Only thing we have to remember is that in such cases we have to use an AC source, fact number 1. Fact number 2 is that so the output voltage is actually also going to be an AC. So it is not going to be a DC. So we have to extract the amplitude of this wave somehow, right? And not only that, if we are going to measure a time varying signal, then this amplitude of the wave will actually vary in some ways, sometimes maybe decreasing, sometimes maybe increasing. So we have to, if we have to get the actual signal out, then we have to track this variation of the amplitude and actually reject this sinusoidal variation, which is purely due to the excitation source. We will have to reject, right. So we will see in this lesson towards the end how that is rejected, right. So apart from this bridge functions exactly like a resistive bridge. Now, so then we come to the second element, which is an extremely important element in analog signal conditioning, which is the operational amplifier. So the operational amplifier is actually a circuit made of transistors which behaves in a nice manner. It actually behaves like very close to an ideal amplifier. So it has two input terminals. This one is called the non-inverting input, another is called the inverting input, marked by plus and minus, and the output is actually proportional to the difference between non-inverting and inverting input. Now this gain is generally, now obviously all voltages in circuits are limited by their power supply voltages. So and this gain is also very high, so therefore it is not that we are going to get hundreds of voltages output from here. What is going to happen is that within a small range this will behave like this equation, so it will be like a straight line. After that, when it reaches close to the power supply voltage, then it will get saturated. So this is a real operational amplifier characteristic. Now so if you see, actually ideally operational amplifiers have some characteristic, but real operational amplifiers actually have characteristics which are very close to the ideal characteristic. That is why operational amplifiers are so extensively used, right. So for example, the input impedance of the amplifier is ideally infinite. Ideally it has an extremely high, rather the open loop gain is infinite, that is the value of G is very large. Typically you will get of the order of 10 to the power 6, actually this 10 to the power 4 is a rather low value. In modern operational amplifiers you have 10 to the power 6, 10 to the power 7, even higher ranges sometimes. Then you have infinite, the input impedance is actually very high, so it does not draw any current, does not load the source, and you can get, for some kinds of amplifiers you get even thousands of gigaohms resistance. The output impedance is typically very low. It's ideally supposed to be 0, but typically it can be, depending on the current capability of the amplifier, it can be between 10 ohms and 5 kilo ohm is actually a high value. You get something like 100 ohms, around 100 200 ohms all the time. So the implications is that naturally, you see, with such a high input gain you cannot really use it in open loop, because then you have to apply very small voltages, especially in analog signal conditioning. So the operational amplifier is typically used in open loop only in the case of only when it is used as a comparator, but not otherwise. And it is generally used with feedback. It is generally used with feedback. So when you connect a high gain amplifier in feedback, then its gain becomes very stable and only determined by the external component. So this property is used, which we'll presently see some of these. So the first configuration that we are looking at is an inverting gain amplifier, where, so you see, this is the operational amplifier element. Along with that, it is now connected to these external elements R1, R2. This is the load resistance, and one of the terminals is, this is called the non-inverting input. Since the actual signal input is actually coming to the inverting terminal, and because the voltage, so if you apply a positive voltage here, you will get a negative voltage here. That is why this amplifier is called an inverting amplifier or an inverting gain amplifier. So as we know that by virtual ground principle, since this, I mean the basic principle is simple, since the open loop gain is very high, and if this voltage has to be finite, then this potential difference must be 0. So this is called the virtual ground principle. Since this is in ground, therefore this is also at ground, very close to ground, and that it is maintained very close to ground by the feedback, right. So what is the current flowing into this? The current flowing into this is Vm by R1. Now since the amplifier presents a extremely high input impedance, therefore no current is flowing into this. So therefore this same current is flowing into this. This is at ground, so therefore this potential is minus I into R2 is equal to, what is I? I is V by R1, so it is minus R2 by R1 into V. So this is minus R2 by R1 is the gain, right. So this is called the inverting gain amplifier. It is very simple, requires only 2 resistance elements. Only drawback is that the input impedance seen by the source is this resistance. So V by R1 is the current flowing into it. So this resistance, if this resistance is low, then this overall amplifier has a low input impedance, right. So now we go for another the non-inverting gain amplifier configuration. So in the non-inverting gain amplifier configuration, see that this is actually wrong. So this should be plus and this should be minus. In fact, you can ponder, this is a very interesting question, that what if this was minus and this was plus? Then you would have a case of positive feedback and the circuit would not have behaved like a linear amplifier at all. So anyway, we are not discussing that case, but this is plus, this is minus. So now you see that here what happens is that, so this potential, now no current is flowing into it. So this amplifier, one of the plus points is that this amplifier has very high input impedance, equal to that of the basic op amp. And since by virtual ground, so then for this potential is V in, so therefore this potential is also V in, right. So you can easily calculate just by solving the DC network that V0 will be given by 1 plus R2 by R1 into Vi. So the gain of the inverting amplifier is 1 plus R2 by R1. Note that there is no minus sign, therefore it is a, rather than it is a non-inverting amplifier, right. So then we, in many cases in instrumentation, we need to add up signals. You need to, for example, you can take sensors. Suppose you want to compute the average value. You actually have put 2 sensors which are both measuring temperature, and you want to measure the average temperature. So then what you have to do is you have to add, you have to multiply each one of them by a gain, say 1 by n, and then add all of them, right. So that requires a summing amplifier. So this is a particular summing amplifier. In this case it is a summing and inverting amplifier, because you see that we have basically taken the inverting amplifier configuration. Only thing is that now we are connecting 2 sources, so V and VB, and 2 currents are being, this is still at 0 potential because of virtual ground. So now we are pushing 2 currents, so this is I1 and this is I2, and those 2 currents are flowing through this. So therefore this potential is going to be at minus of I2 plus I1 into RF. So we will get, so it is equal to minus VA into RA by VA by RA, rather VA into RF by RA minus VB into RF by RB. So this is one of the weights, this is the other weight. So you have, this is equal to V0. So you have summed 2 voltages, input voltages, and weighted them by 2 gains. So it calculates a weighted sum of 2 signals, correct. So now we go for, similarly we can have a difference amplifier. Now see, this configuration is slightly different in the sense that one of the amplifiers are one of the sources are connected to the non-inverting input through a resistance network, and the other is connected to the inverting input. So it's a combination of inverting, non-inverting, right? And also note that the resistance values are made equal. So what happens, what is the result is that you get that V output is equal to R2 by R1 into V2 minus V1. So you purely calculate the difference. So very interestingly you see that it does not depend on the value of V1 or the value of V2, but depends only on their difference. So they can be 10 volts and 9 volts, or they can be 2 volts and 1 volt, and still the output is going to be the same. And there are many cases where this amplifier is used, because in many cases what happens is that we want to have an amplifier where the value of we only want to amplify or take as the signal, as the output signal, which is the difference of two potentials and not the individual potentials themselves. So that's what you do by the difference amplifier. Only disadvantage of this amplifier is that again the input impedance seen by these amplifiers are low. So we need to improve on the input impedance, and there is also a particular factor for difference amplifiers which is called the CMRR, or the common mode rejection ratio. That is, although I am saying that it is not dependent on the levels of these individual voltages but only on the difference, actually what happens is that the output becomes actually is proportional to some difference gain into V1 minus V2, and then some common mode gain, it is not completely dependent on this, into V1 plus V2 by 2. So the whole exercise in circuit design is to make this gain small and this gain large, then it will behave like an ideal difference amplifier. So circuits are available with very high CMRR values. Now we come to a circuit called the integrator. So if you want to integrate, what we do is we put a capacitor here. So now this current flowing will now still flow through this switch is open when it is working. So therefore the output will be 1 by RC into integral 0 to T V in dt. So the output voltage, in the output voltage we have produced a voltage which is proportional to the integral of V. This is also very much necessary in a number of instrumentation applications. For example, we may like to integrate flow to get level, or to compute total sum of flows, I mean so many things. So integrate velocity to get position, etc. This reset switch is added such that the initial condition on the capacitor can be nullified, can be made 0 before the circuit starts operating. Now we have what is known as the instrumentation amplifier. So the instrumentation name comes directly into play, because these signals can accurately, this signal firstly it offers a very high input impedance. Secondly, the input impedance is also symmetric. In the previous case it was not symmetric. If you see from the inverting input, you will see one input impedance. If you see from the non-inverting input, you will see another input impedance. But in this case the input impedance is symmetric. You can if you examine this circuit, you can find out that this is nothing but an difference amplifier stage. This is difference amplifier. Along with that, an input stage is added. So the input stage, the basic job of the input stage is to do three things. Number one is increase input impedance. So you see each one of these inputs are feeding into the non-inverting input, so they see a very high input impedance. So there is no question of loading. Second thing is that the input impedances seen are equal, they are not different. Third thing is that normally in this resistance, if you see commercial instrumentation amplifiers, you will find that the gain of the input stage can be programmed. Generally the gain of the differential amplifier stage is not disturbed. It is because the differential amplifier is typically designed for having very high CMRR, and that stage is generally not disturbed, while if you want to program the gain, you program by programming this resistor either by connecting jumpers or by connecting external elements. So this is an instrumentation amplifier, and So now it has a, it will have the gain of this will be, you know, the product of these obviously. So you can learn more about it. Next we have a charge amplifier. So you see that there are certain cases where we need to produce a voltage which is proportional to the charge. For example, as we have seen in the piezoelectric crystal, that the piezoelectric crystal produces charge which is proportional to the force applied or the displacement of the piezoelectric crystal surfaces, right. So in this case you can see that now if you, in this case the input signal is actually assumed to be pressure. So we have put P dot. So if you consider this P dot as a, P produces charge, so P dot or the derivative of P will produce current, derivative of charge. So therefore this is modeled as a current source. Now you see that this current will actually flow into this path. Why not this path? Because of the fact that these resistances, because this is an amplifier, so this is maintained by virtual ground. So this resistance potential difference is nearly 0. So therefore with the impedances here, the current flow into these impedances is actually going to be negligible. So most of the current, so actually this is the low impedance path, and therefore the current will flow into this capacitor and will get integrated. So when it will get integrated, this is pressure dot, so the output voltage is going to be proportional to pressure. So this is very highly used in piezoelectric crystals, also because of the fact that even if these resistances vary, it's not going to affect the result. So you can connect a cable and the cable capacitance does not affect the sensitivity of the device, as we have seen in the case of piezoelectric. Next we talk about an isolation amplifier. You know, there are certain cases where the input sensors may be at some, you know, some very high voltages. For example, suppose we want to measure a motor current. Now we typically what we do is we take the winding of the motor, and in series with the winding sometimes we just connect a resistance and we tap this voltage just to sense the current through the motor winding. So now this, although this potential difference is actually proportional to the current, but these can be, these points can be at very high potentials compared to ground at hundreds of volts. So therefore it's important that you don't directly connect these such signals into your electronic circuits. It will even damage the circuit. So for such things isolation amplifiers are used. So there are various ways of isolation. There are optical ways of isolation, there are transformer coupling of isolation. So in the isolation amplifier, from the input side and the output side, there is no galvanic electrical connection. So the signal is transmitted from one side to the other by some other means. In this case it is the mutual inductance or flux linkage. So what happens is that the input is applied here. See, this part is actually floating, this part is not connected to the ground of the circuit at all. So therefore there is no problem applying high voltage here. So the input is amplified with these resistances and then applied to this. This is the input is actually applied with a phase sensitive modulator, because this is a transformer coupling. So therefore it has to be AC. So therefore basically a sine wave is modulated by the input. So the amplitude of the sine wave goes up and down as the input increases and decreases. So that sine wave is actually applied to the primary of the transformer. So as we shall know that in the secondary we will get the same wave, only we will get it by some turns ratio. So we get it, so in the secondary we get the same wave, but see that there is no electrical connection between the primary and the secondary. So therefore the secondary side grounds and reference potentials are completely different from the primary side ground. So now this signal is taken and passed through a phase sensitive detector. We will see what it is, which will strip it of that sine wave which was added here, and then it so this PSD and low pass filter will finally extract this signal which we applied, and then it will be passed through. This is nothing but a buffer. So it will be applied to the buffer, and then we'll get the voltage out. So you see that this is called an isolation amplifier, because the input side and the output sides are said to be completely ohmically or galvanically isolated. So this is another kind of amplifier which is often used. Then in some cases, for example, we need to do various kinds of computation, like for example, we may be interested in sensing a voltage and a current signal and then measuring power, in which case we need to measure, we need to multiply. There may be cases, for example, in the case of flow measurement, as we have seen, that the flow is actually proportional to root over of delta P, and what we sense from a meter is essentially delta P. So we need to compute root over of delta P. So for such signals, as we know that a logarithmic amplifier is of great use, because if you take a, if you want to have a multiplier, then if you take the log, then it becomes, in the log domain it becomes an addition. So you can actually first compute the log of signal A, then compute log of signal B, then add them. So you get log A plus log B, which is equal to log AB, and then you pass it through an anti-log amplifier, which will give you AB. So you have multiplied using two log amplifiers, one normal summing amplifier and an anti-log amplifier. So this is the principle which is used, and the logarithmic and the anti-log amplifiers are basic building blocks of that. And in the logarithmic amplifier, we will not go into a detailed derivation of the circuit, but the basic idea is that you see this, look at this transistor. See, this transistor is here, the collector and the base are shorted. So therefore this is behaving like a diode. Here also, see, this is at virtual ground, this is also at ground. So here, so effectively this collector and base are also shorted. So these are two diodes actually, these are two diodes. And we know that in diodes the current is what is the voltage current relationship. So the voltage current relationship is I is equal to some I naught into some e to the power V by some constant, say V by Vt. So you see that the current, so actually the voltage is proportional to log of the current. So if you can generate a voltage in the output, which is, so now if this current is actually proportional, so in this case see what is the current, what is the input current? The input current is Vs by R1. So the input current is actually proportional to the voltage, input voltage. So the output voltage, if we can use this amplifier, the output voltage is going to be proportional to the log of current, or it is going to be proportional to the log of the voltage. So this is the basic principle, and in which we use this log amplifiers. And for example, for this circuit, there are certain assumptions which you can make, that is which are actually valid, and then you will get that the output is actually proportional to, see, this is a constant, and this is, so is proportional to some constant time log of the input voltage. So this is the logarithmic amplifier, and exactly opposing, just by using the same principle, one can also construct an anti-log amplifier. Actually this circuit is, as it is drawn, is erroneous. This line will not be there, this line should be deleted. So you see, again we have a diode here, and we have again, because of this virtual ground, we have a diode here. So in this case you can understand that again the voltage here, at this point is actually proportional to Vs. It is actually R3 by R4 plus R3 into Vs. So therefore, since this is connected in negative feedback, so therefore at this potential also you have at this point also you have the same potential, and so the current that is flowing, that it cannot flow into this, so therefore it will flow entirely through this diode, and the output voltage will be such that the current that is flowing will be also entirely through this diode. So using these principles you can find out that the opposite effect can be achieved if you write the equations. So, and the output voltage in this case becomes exponential of Vs, so it is an anti-log operation. Okay. So now we come to the the other important block which is called filter. So we have various kinds of filters. For example, filters are basically frequency selective networks. So as we all know that any arbitrary waveform can be always thought of as a sum of sinusoidal waveforms of various frequencies, right? And the job of the filters is that they will allow some of the frequencies, or they will amplify some of the frequencies, and they will not allow some of these frequencies. So they are frequency selective. So some frequency, for example, it often turns out in instrumentation we are interested in accurately measuring signals. So in many cases the process variable that we want to measure is actually a slowly varying quantity. So it has only low frequency components. On the other hand, while we are acquiring the signal, maybe it is going through a cable, maybe somewhere some high frequency noises like from the power lines, etc., are getting into the signal. So we would like that we can separate out the signal of our interest and these undesirable signals like these powered signals. So if you want to do that, for example, we can say that okay, our signal is within 1 hertz, actual signal. Power signal is 50 hertz. So can I have a network which will have nearly zero gain at 50 hertz and quite good gain at 1 hertz. Then if I pass my noisy signal through it, then the power frequency signal will be killed and the real signal will be passed. So this is the basic purpose of filters. So they are actually frequency selective networks, and there are various types of filters. So for example, we have low pass filters in which we pass low frequency and stop high frequency. We have band pass filters where we only pass within a certain band from some frequency f min and f max. The lower than f min are also rejected, higher than f max are also rejected. Such filters are called band pass. Similarly, we have high pass in which we reject below a certain level. For example, suppose we know that we don't have any DC signal in our actual case. Like for example, typically when we measure vibration, we cannot have a DC signal in vibration. Vibration signals are always kind of high frequency. So there's no, so we can eliminate, but some DCs may come due to other kinds of biases. So we can eliminate them using high pass. We can also have some band reject. So for example, I was saying that we can reject 50 hertz. So we can create a filter which will just reject, have very low gain around 50 hertz and good gain around on both sides of it, low and high. Such filters are called band reject. Notch is nothing but a narrow band reject. And all pass, sometimes we have all pass signals where we are not interested in changing the gain, but we are interested in changing the phase. So these are being mentioned typically because they are the major types of filters, but typically the low pass, band pass, high pass signals are mainly used, low pass being the most common. So if you see in the domain of transfer function, then if you see second order transfer function, then this is a typical low pass transfer function. You can find out that it is low pass because if s tends to infinity, then the denominator becomes very high and the value of Ts, which is the gain of the filter, becomes nearly 0, while as s tends to 0, the gain of the filter becomes d by b, which is a constant. So at low frequencies it has a constant gain, but at higher frequencies the gain falls and approaches 0. For high pass, on the other hand, there is an s squared term on the top. So when s tends to infinity, it becomes m. M is the high frequency gain, which is constant, and as s tends to 0, because the denominator tends to b but the numerator tends to 0, so the gain goes to 0. So this is high pass, right? Similarly, you have a band pass in which you can see that if s tends to 0, then also this gain tends to 0. If s tends to infinity, then it becomes s, and this s squared terms become dominating. So this becomes cs by s squared. So again it goes to 0. So on both sides, for very low values it is 0, for very high values it is 0. In between it has a gain. Therefore it is band pass. In this case, this is band reject, because if you have s close to d, then you can see that this s squared term, if you put, normally we put s is equal to j omega. So then you have a term d minus omega square. So as omega approaches root over d, the gain of the filter will fall, right? And as omega tends to infinity, this gain is 1, and as omega tends to 0, this gain is d by b. So on both sides you have good gain, suddenly around d the gain will fall to 0. This is a band reject filter. There are various ways in which filters are realized. You can have purely passive networks, RLC networks for realizing filters, but most modern filters are realized using RC elements, and because that's what is typically used in electronics, and using amplifiers because you simultaneously want to have a certain amount of gain in the filter. This is a very well known architecture called the Sallen and Key low pass filter. So it turns out that this is a low pass architecture. In fact, you can have a Sallen Key low pass high pass filters. In fact, if you change the resistances and the capacitances, if you interchange them, then the filter transfer function goes from low pass to high pass. So in the Sallen Key filter, the transfer function is given like this, where this k is actually the gain of the last op amp block, which is 1 plus R2 by R1, because it's a non-inverting block, if you have noticed. So you see that it is obviously from the transfer function we realize that it is a low pass transfer function. The top is constant and the bottom you have a second order polynomial in S. So you can see that that is for second order transfer. What is the, whenever we have a filter, we are concerned with what is the pass band and what is the stop band. So we want to know that which are the bands in which we can assume that the signal will be passed with good gain, constant good gain, and which are the bands in which the signals will be stopped. So while the stop is not abrupt, in fact you can make it more and more abrupt by designing more and more complex filters of higher and higher order, but generally the gain will fall continuously. So at some point we say that okay, we call it a bandwidth. Okay, so we say that if the low frequency gain falls by a quantity called 3 dB, or when the low frequency gain becomes 1 by root 2, then we call that a 3 dB bandwidth. So that's a term which roughly signifies that up to what frequency the gain will be more or less high. So that is given by, in this case, 1 by R1 R2 C1 C2. So generally what order filter you will design, etc., depends on the application itself. So using low pass and high pass filters you can very easily construct band pass filters. For example, see, it's very simple that this is a low pass first order transfer function. You can see that is low pass, you can take it as S, and then as S tends to infinity this gain will go to 0, so it does not pass high frequency. On the other hand, this is high pass because this is another S and this is another S. So as S goes to 0, this goes to 0, but as S goes to infinity, this will go to 1 nearly. So you can see that what we have done here is that we have cascaded a low pass and a high pass, and we are ensuring that the cutoff frequency of high pass is actually lower than the cutoff frequency of low pass. So if you see on the frequency axis, then the cutoff frequency of the low pass is like this, and this for the high pass, and this is lower than the cutoff frequency of the low pass. So you see that when you multiply them, around here the gain is 0. Why? Because the high pass gain is 0, they are in series. Around here the gain is almost 0 because the low pass gain is 0, and in between there is a frequency band in which none of them are 0 and they are substantial, and you get a gain. So you get a band pass filter by cascading a low pass and a band pass filter and ensuring that the cutoff frequencies of the high pass is lower than that of the low pass. So this is a simple way of creating a band pass filter. Band pass filters are very often used in vibration monitoring instruments, which are widely used in industries to check the health of rotating machinery like turbines, motors, large motors. So similarly, if you can have a see, so this is the circuit implementation. So you have a low pass and you have a high pass. Now only one thing is to be remembered, that what is to be remembered is that there is a loading effect, meaning that just because this has a low pass transfer function G1 and this has a transfer function G2, this resulting transfer function is not going to be G1 G2 exactly because of what is known as loading. So if you want to prevent loading, you can put a buffer here. Otherwise it's going to be still it's going to be a band pass, but it will be slightly different than G1 G2 because of electrical loading, because this side is not open. When we derive this transfer function, we assume that these ports are open, but this is not open. So it will see the effective impedance of this branch will be this in parallel with this. So that will happen. So this is a band pass, typical band pass plot as we have shown. Low at the low frequencies, low at the high frequencies, and in between high. Similarly, you can have a band reject filter. This is a band stop filter. So if you have a band stop filter, and if you have now the cutoff frequency, now if you have the cutoff frequencies where the omega high pass, so this is low pass and this is high pass. So now cutoff frequency of high pass is actually higher than the cutoff frequency of the low pass. So now if you actually see, so if you connect these two filters in parallel now, in parallel, so then what will happen is that at the low frequencies, this low pass filter channel will pass. So the signal will pass in the low frequencies. At the high frequencies, now the filters are in parallel, as we will see. So in the high frequency, the high frequency channel will pass the signal. But in between, since both gains are 0, so therefore none of the channels will pass, and you have what is known as a band stop filter. So that is what is shown here, that low pass and high pass are shown in parallel. So yeah, so Bode plot is also shown. The Bode plot is, the Bode plot, you can see that it falls down at some frequency, so it rejects this stop band. Oops. Now, so we have seen the amplifiers and we have seen the filters. So now we look at two other types of signals which are very common in instrumentation. For example, it is very common that the sensor signals are all analog, but it is very common nowadays that you would like to acquire those signals into a computer or some sort of a digital computing hardware and then process it further and maybe send it by some communication means, etc. So the step that has to be achieved for that is that you have to generally what you do is you connect it to some sort of a data acquisition hardware which actually takes as input the analog signals and produces as output a set of digital signals which are read by the computer on the bus and then stored on the memory, etc., etc. So there are large number of such devices. You get such data acquisition cards, you get data loggers. So all these things are used in instrumentation widely. So we are going to see how this thing basically takes place. So we have an analog filter and we have an analog signal here, not an analog filter, and we finally want to produce its digital equivalent, right? So it turns out that obviously at the final stage we need an A to D converter, AD converter. So but it turns out that you need to sample the signal from time to time, and it also turns out that you need to put a filter before you put the sample and hold amplifier. This is related to the fact to an effect which is called aliasing. So therefore you need to actually put an anti-aliasing filter which is simply a low pass filter and whose cutoff frequency is related to the sampling frequency which you are using here. And the sample and hold amplifier basically takes certain values of signals and then holds it constant, again takes a value of signal, again holds it constant. So it samples the signal and then holds it constant in between. So you need to put these three typical blocks: an anti-aliasing filter, then followed by a sample and hold amplifier, and then followed by an ADC. So this is a sample and hold amplifier. So you can see that this is basically a MOS where so you can see that this is basically a MOS. So if you turn on this MOS, this is a buffer, so this voltage will actually come and charge this capacitor, and then if you switch off this MOS, then there is no way that this capacitor can discharge. This side is also open, this side is also high impedance. So this voltage on the capacitor will be held if you keep it discharged. So this voltage will be held here. So every time you want to sample, you turn this on, this signal will be transferred here, then you turn it off, it will be held. So this is called a sample and hold amplifier. Lastly, we have a phase sensitive demodulation circuit where we have a modulated wave, it is, and then we have to demodulate it, right? So a modulated wave is typically looks like you have a signal xt sine omega t. So you have a signal xt and xt sine omega t will look like this. Yeah. So you want to, from there you have to extract this xt signal and you have to reject this sine omega t signal. This is the problem of demodulation. So what will happen? So what will happen is that, so what you do is you actually multiply this signal by see. So we'll skip this, and so actually what we'll do is we will talk about this little bit in our next lecture and straight away go to the lesson review. So this phase sensitive demodulation, we will talk about it in the next lecture. So in the lesson review, we have talked about Wheatstone bridges, we have talked about amplifiers, we have talked about various kinds of filters, and we have talked about sample and hold amplifiers in the lecture, and the phase sensitive demodulation we will talk about it in the next lesson, lesson 10. So points to ponder, you can think about what should be the bridge ratio for a single arm resistance temperature bridge. It should be low because of the fact it should be, well, you should decide that because the temperature is, the resistance change in an RTD bridge is quite high in contrast with the sensor with the strain gauge bridge. Then explain the main merits of the instrumentation amplifier circuit, we have discussed this already. Give one example application of high pass filters in instrumentation. You can think of something where there is no low pass signal, it is the noise. And why is an anti-aliasing filter at all needed before sampling? For this you have to learn what is known as the Nyquist sampling theorem. So that is the end of the lesson today. Bye bye.